Engines lesson. In this lesson, you will learn about the aircraft's two engines and their respective components and controls. In addition, we will review both normal and non-normal engine indications. The airplane is powered by two Rolls-Royce Trent 1000K engines. The engines are each rated at 73,800 pounds of takeoff thrust. The engine is a three-rotor axial flow high-bypass turbofan engine. The rotors are designated N1, N2, and N3. The N1 rotor consists of the following items on a common shaft: a fan and a low-pressure turbine section. The N2 rotor consists of the following items on a common shaft: an intermediate pressure compressor section and an intermediate pressure turbine section. And the N3 rotor includes a high-pressure compressor and a high-pressure turbine. All three rotor assemblies are mechanically independent from each other. An engine accessory gearbox is driven by the N2 rotor. Each engine is controlled by an electronic engine control, or EEC. The EECs monitor autothrottle and flight crew inputs through the thrust levers to automatically control the engines. Engine controls are located throughout the flight deck. Review the engine controls before pressing the Continue button to resume the lesson. Primary and secondary engine indications are provided on the ICAS display. The ICAS is normally displayed on the inboard MFD window of the captain's or first officer's inboard display unit. The ICAS display can be swapped between the captain or first officer inboard display unit by selecting the ICAS transfer switch on either display select panel. Engine indications can be presented as digital readouts, round dials with moving pointers, or vertical indications with moving pointers. The digital readouts display numerical values, while the moving pointers indicate relative value. If engine data is not available, the associated engine indication blanks. There is no ICAS message relating to the loss of engine data. The normal operating range on a dial or vertical scale is displayed in white. The oil temperature, oil pressure, and EGT indications have caution ranges displayed by amber bands. Operation in the amber band will change the color display of that indication. For example, if oil temperature reaches the caution range, the digital readout box, and pointer change color to amber. The indication changes color back to white when it returns to the normal operating range. N1, N2, EGT, oil pressure, and oil temperature indications have operating limits, indicated by red lines. If one of these indications reaches the red line, the digital readout, dial, box, and pointer change color to red. The N3 indication does not have a range or red line limit, but will change to red if the operating limit has been reached. The oil temperature and oil pressure indications change color back to white when they return to the normal operating range. When N1, N2, N3, and EGT return to the normal range, the indications return to white, but the box remains red as a reminder of the exceedance. The red box color can be canceled or recalled by pressing the Cancel Recall switch on the DSP. The primary engine indications are always present on the ICAS display. The primary engine indications are TPR, N1, and EGT. The turbofan power ratio, or TPR gauge, is the primary thrust reference indication. The following items are displayed on the TPR indications: maximum TPR amber line, reference target TPR, commanded TPR sector, reference TPR, actual TPR, and actual TPR indication. Review the TPR indications before pressing the Continue button to resume the lesson. The N1 indications include the following: N1 red line, N1, and N1 indication. Review the N1 indications before pressing the Continue button to resume the lesson. The following items are displayed on the EGT indications: EGT red line, EGT amber band, EGT indication, EGT start limit line, and EGT. Review the EGT indications before pressing the Continue button to resume the lesson. Secondary engine indications are displayed on ICAS below the primary engine indications. The secondary engine indications can be displayed by pushing either secondary engine display switch on the Display Select panel. The secondary engine indications are N2, N3, fuel flow, oil pressure, oil temperature, oil quantity, and engine vibration. The secondary engine indications are automatically displayed when the displays initially receive electrical power, a fuel control switch is moved to cutoff in flight, an engine fire switch is pulled in flight, a secondary engine parameter is exceeded, engine N2 RPM is below idle in flight, a start selector is in the start position, or the fuel flow engine left or right advisory is shown. When secondary engine parameters are automatically displayed on ICAS due to any of the above conditions, they cannot be cleared until the condition is no longer present. After the condition is resolved, the secondary engine parameters can be cleared by pushing the engine display switch. The N2 indications include the following: N2, N2 red line, N2 indication, running indication, starting mode, and idle target indication. Review the N2 indications before pressing the Continue button to resume the lesson. The N3 indications are shown as a simple digital readout. This display will change to red if the operating limit is reached. Review the N3 indications before pressing the Continue button to resume the lesson. The fuel flow indications are digital readouts only. Review the fuel flow indications before pressing the Continue button to resume the lesson. Oil pressure and temperature indications are a combination of digital readouts and vertical indications with moving pointers. The following items are displayed on the oil pressure indications: oil pressure amber band, oil pressure pointer, and oil pressure red line. Review the oil pressure indications before pressing the Continue button to resume the lesson. The following items are displayed on the oil temperature gauge: oil temperature red line, oil temperature amber band, and oil temperature pointer. Review the oil temperature indications before pressing the Continue button to resume the lesson. The oil quantity in liters is shown as a digital value only. Review the oil quantity indications before pressing the Continue button to resume the lesson. Engine vibration indications are a combination of digital readouts and vertical indications with moving pointers. The following items are displayed on the engine vibration indications: engine vibration, vibration source, engine vibration pointer, and engine vibration high band. Review the engine vibration indications before pressing the Continue button to resume the lesson. Each electronic engine control has full authority over its respective engine operation. The EEC uses thrust lever inputs to automatically control forward and reverse thrust. The EEC has two control modes: normal and alternate. In the normal mode, the EEC uses TPR as the parameter for setting thrust. In alternate, N1 RPM is the thrust reference parameter. During normal operations, the EEC is powered by a dedicated permanent magnetic alternator, or PMA. For engine start, initial EEC power is supplied by the airplane electrical system. The airplane also serves as an alternate EEC power source whenever a PMA is unavailable. In the normal mode, the EEC sets thrust by controlling TPR, based on thrust lever position. TPR is commanded by positioning the thrust levers either automatically with the autothrottles or manually by the flight crew. The EEC also continuously computes a maximum TPR value. Maximum TPR represents the maximum rated thrust available from the engine based on air temperature and pressure altitude. Maximum rated thrust is available in any phase of flight by manually moving the thrust levers to the full forward positions. If the required signals are not available to operate in the normal mode, the EEC automatically switches to the alternate mode. In the alternate mode, the EEC schedules N1 as a function of thrust lever position. No thrust protection is available in the alternate mode. When the EEC initially switches an engine to the alternate mode, and the associated mode switch is in normal, the EEC enters the soft alternate mode. In soft alternate, the EEC uses a snapshot of the last known ambient conditions to calculate maximum N1 data. In this mode, the TPR indication blanks and the N1 display remains the same. On the mode switch, both normal and alternate will be illuminated. When the EEC mode switch is pushed, the normal light extinguishes, and the engine switches to the hard alternate mode. In hard alternate, the EEC sets thrust using N1 and an alternate pre-programmed thrust schedule. The N1 indication changes to include reference and target N1, maximum N1, and commanded N1. The engine EEC mode left or right advisory message illuminates anytime the engine is in an alternate mode. When operating in soft or hard alternate mode, the autothrottles will remain connected. If only one engine has changed to alternate mode, selecting the alternate mode on the other engine will eliminate thrust lever stagger or asymmetric thrust. The alternate mode thrust schedule provides equal or greater thrust than the normal mode for the same thrust lever position. Since thrust protection is not provided in the alternate mode, maximum rated thrust is reached at a thrust lever position less than full forward. As a result, thrust overboost can occur at full forward thrust lever positions. Advancing the thrust levers to full forward while in alternate mode should only be considered during emergency situations when all other available actions have been taken and terrain contact is imminent. The ICAS caution message, engine limit protection left or right, is displayed if the thrust lever position commands an N1 greater than the maximum rated thrust or maximum N1. The EEC monitors N1, N2, and N3 rotor speed to provide overspeed protection. If N1 or N2 rotor speeds approach the red line limit, the EEC commands a reduced fuel flow. When RPM limiting is in effect, the ICAS advisory message, engine RPM limited left or right, is displayed. If the red line limit is exceeded, the ICAS caution message, engine limit exceed left or right, is displayed. If RPM limiting fails and an overspeed condition persists, the EEC commands fuel shutoff to shut down the engine. Once the engine falls below idle speed after shutdown is commanded, the ICAS caution message, engine fail left or right, is displayed, and an aural beeper sounds. Each engine includes a secondary air system, or SAS, that provides cooling and sealing airflow to the intermediate pressure turbine. Air for this system is provided by intermediate pressure air from stage 8 and high pressure air from stage 3. A secondary air system valve, or SASV, regulates the air from these two stages. System control and monitoring is automatically provided by the associated EEC. If the SASV fails in the closed position and the engine is at idle speed, the EEC automatically commands a higher engine idle speed. This prevents ingestion of turbine annulus gases into the SAS system. When on the ground and below 80 knots, this is indicated by the engine control left or right ICAS advisory message. Failure of the SASV in the open position could lead to an abnormally high temperature in the system and overheating of the engine bearings. If the valve fails open, the maximum thrust indication is reduced on the TPR. If this occurs above 400 feet AGL, thrust is automatically reduced to a safe limit, and the thrust command arc on the TPR gauge displays amber. Additionally, failure of the SASV in the open position will be indicated by the following: ICAS warning message, engine thrust high, left or right, displays with siren, and/or the ICAS advisory message, engine secondary air valve, left or right, displays. Thrust control malfunction accommodation is an EEC function that provides protection against idle thrust asymmetry conditions while on the ground. The EEC commands shutdown of the affected engine when the airplane is on the ground, the thrust lever is at idle, and the engine is above idle speed and not decelerating normally. This results in an associated engine fail caution and an aural beeper. Thrust asymmetry protection, or TAP, is an automatic feature that provides protection against asymmetric thrust during takeoff or go-around by limiting thrust on the higher thrust engine. TAP enhances safety by allowing a decrease in approach speed at light gross weights, providing engine-out control capability for speeds above stick shaker, and allowing full rated thrust to be available for all engine operation at all weights and airspeeds. For an engine-out condition, TAP reduces thrust on the operating engine to ensure there is sufficient rudder for directional control. TAP reduces thrust when the airspeed decreases below approximately V2 on a takeoff, or below approximately VREF on a go-around. Once speed is increased above V2 or VREF, TAP increases thrust. The TAP function does not affect thrust for engine-out operations flown at or above V2 or VREF, with the exception of a lightweight go-around at less than 152,273 kilograms, where TAP reduces thrust slightly at VREF on the go-around. In the following example, the right engine has failed and TAP is actively reducing thrust on the left engine. As TAP reduces thrust, the maximum and commanded TPR ticks move down to the reduced TAP thrust value, and the actual TPR indication follows. The reference target TPR indication and the thrust levers do not move. As TAP increases thrust back to normal, the maximum and commanded TPR ticks on the left engine move up until they again match the reference target TPR indication. TAP does not affect certified takeoff performance. For airspeeds where TAP does limit thrust, climb gradient is higher with TAP limiting thrust than it would be if TAP did not limit thrust. This occurs because additional thrust asymmetry creates more airplane drag than the thrust that was added. Therefore, if TAP becomes active due to a speed reduction below V2, any reduction in climb gradient from that scheduled for the takeoff is due to mismanaged speed and not due to TAP. TAP is only available when the flight controls are operating in normal mode, and the EEC is in normal or alternate modes. If the TAP function is inoperative, the ICAS advisory message Thrust Asymmetry Protection is displayed. The EEC will automatically command different idle power settings depending on certain conditions. Possible idle settings include minimum idle, approach idle, icing idle, and ice crystal idle. Minimum idle. Minimum idle is selected for ground operation and most phases of flight. Approach idle. Approach idle has a higher thrust than minimum idle. This decreases acceleration time for go-around. Approach idle is selected in flight when the flaps are commanded to 25 or greater and the landing gear is selected down. Approach idle is maintained until after touchdown when the EEC selects minimum idle. Icing idle. Icing idle is selected when engine anti-ice is on and is approximately the same setting as approach idle. Ice crystal idle. Ice crystal idle is selected in flight when outside air temperature is between ISA and ISA plus 29 degrees Celsius, or altitude is between 35,000 and 5,000 feet. The thrust management function of the flight management computers uses environmental and performance data to calculate engine thrust reference limits. These limits provide engine thrust reference values for specific flight phases. Thrust reference limit modes and TPR values are displayed on and above the ICAS TPR gauge. Available thrust reference modes include takeoff, climb, continuous for non-normal conditions, cruise, and go-around. When VNAV is active, thrust reference limits sequence automatically when changing phase of flight. Thrust settings can also be selected manually via the thrust limit page on the CDUs. The normal takeoff thrust reference commands engine TPR to 100% rated takeoff thrust. However, takeoff thrust can be reduced to lower operating EGT and extend engine life. Two methods may be used to limit takeoff thrust: derate and assumed temperature. Takeoff limit thrust reductions are selected on the thrust limit CDU page. If takeoff 1 or takeoff 2 is selected, the maximum rated engine thrust will be decreased by 10% or 20% respectively. The select prompt moves to the selected derate. The ICAS thrust reference mode changes to takeoff 1 or 2, and the reference and target TPR indications decrease. Derate thrust setting parameters are considered a limitation. Thrust levers should only be advanced past the limit TPR value in an emergency situation. Assumed temperatures are entered in the Select OAT field on the thrust limit page. Entering an assumed temperature that is higher than the actual temperature will reduce the reference takeoff thrust limit. The maximum authorized thrust reduction is 25% below the certified rating. When an assumed temperature is entered, the thrust limit mode displays DTO. Assumed temperature is not a limiting thrust factor. If conditions are encountered during takeoff where additional thrust is required, the crew may manually apply full thrust. two derated climb thrust limit options are available from takeoff to 30,000 feet. Climb 1 reduces normal climb thrust by 5%, and Climb 2 reduces normal climb thrust by 15%. Derated climb thrust can be selected manually on the thrust limit page or automatically based on the combined takeoff thrust reduction using derate and assumed temperature. If the total takeoff derate percentage is less than 5%, normal climb is selected. Between 5% and less than 15%, Climb 1 is selected, and 15% or more, Climb 2 is selected. Each engine has two igniters. The EEC automatically selects the appropriate igniter for successive engine ground starts. Dual igniters are always used for in-flight starts. Ignition is controlled through the fuel control switches. Aircraft-supplied DC power is the normal power source for ignition. Standby power provides a backup power source for energizing the igniters. The electrical system powers two starter motors mechanically connected to the N2 shaft via the accessory gearbox. The starter motors are controlled via the start selectors. During engine starts, power to run the starters is drawn from the airplane's electrical system. There are two normal power sources that can provide starter power: the APU and forward external power. Normally, APU power is used to drive the engine starters. Simultaneous engine start is only allowed when the APU is running and both APU starter generators are operational. If both engines are commanded to start with an inadequate power configuration, the second start command is ignored. In the event both starters on the respective engine fail, starters will display across the respective starter symbols on the electrical synoptic, and the ICAS displays the advisory message engine starters left or right. Auto start operation automatically sequences fuel and ignition during start, with no input from the pilot. The engines can only be started using the auto start system. The auto start sequence is initiated by rotating the start selector to start and moving the fuel control switch to run. For in-flight windmill starts, the auto start sequence is initiated by moving the fuel control switch to run. The start selector applies electrical power to the starter motors to begin dry motoring the engine. Additionally, the spar fuel valve opens when the start selector is moved to start. The spar fuel valve will also open if the fuel control switch is moved to run. Positioning the fuel control switch to run will command the EEC to open the engine fuel valve, and energize the igniters at the appropriate N3 RPM. While the EEC is in auto start mode, auto start is displayed in white above the N2 indication. The auto start indication blanks when the system is no longer attempting an engine start. When the engine reaches idle speed, the EEC will command starter cutout. The start selector releases to the normal position, and running is displayed in green above the N2 indication for 30 seconds. During ground starts, the auto start system monitors engine parameters for any of the following conditions: loss of both starters and no N1 rotation. If one of the above conditions is detected, the EEC aborts the auto start sequence without motoring and does not make another attempt. The starters are de-energized and the start selector returns to the normal position. And the ICAS displays the caution message, engine auto start left or right. The auto start system monitors engine parameters and attempts to correct the start for any of the following: compressor stall, hot start, hung start, loss of one starter, no EGT rise, and start time exceeding the starter duty cycle timer. If any of these conditions are detected, the EEC will automatically turn off fuel and ignition, motor the engine for 20 to 30 seconds, then make a second start attempt. This second attempt uses a reduced fuel flow and turns on both igniters. If the second start fails, auto start mode is canceled by the EEC and fuel and ignition are shut off, engine is motored to clear residual fuel, starters are de-energized, start selectors return to normal, and the engine auto start left or right caution message displays. There is a limit of 2 start attempts on the ground. In-flight start envelope information will display on the ICAS when an engine is not running in flight, N2 RPM is below idle RPM, or an engine is shut down in flight and the respective engine fire switch is not pulled. The in-flight start envelope indicates the airspeed range necessary to ensure an in-flight start at the current flight level. If the current flight level is above the maximum start altitude, the maximum start altitude and respective airspeed range are displayed. If airspeed is below the speed recommended for a windmilling start, a starter assist indication is displayed below the N2 indication. Secondary engine indications are also automatically displayed in flight when an engine is not running, N2 RPM is below idle with the corresponding fuel control switch in run, or a fuel control switch is moved to cutoff. For in-flight starts, auto start will continue making successive start attempts until the engine starts, or the pilot aborts the attempt by moving the fuel control switch to cutoff and the start switch to normal if necessary. The EEC monitors engine parameters during a windmilling start to provide the best fuel schedule to ensure the shortest possible start time. Engine auto relight protection is provided for flame-out and sub-idle stall recovery. The auto relight function is activated whenever a flame-out is detected, or the engine is at or below idle with the fuel control switch in run. When activated, the EEC energizes both igniters for the respective engine in an attempt to recover the engine. This also provides protection against flame-out during periods of excessive rain or hail ingestion. The igniters are switched off when the engine reaches idle. Fuel is supplied to the engines by pumps located in the fuel tanks. Initially, the fuel flows through a spar valve located in the main tank. It then passes through the first stage engine fuel pump where additional pressure is added. Next, the fuel is preheated by a fuel oil heat exchanger. After the heat exchanger is a fuel filter that removes any contaminants. The fuel then passes through the second stage engine fuel pump where additional pressure is added. The fuel metering unit, or FMU, adjusts fuel flow to meet thrust requirements. Finally, the fuel flows through a second high-pressure filter before passing through the engine fuel valve and into the engine. The spar and engine fuel valves allow fuel flow to the engine when both valves are open. The spar valve opens when the engine fire switch is in, and either the start selector is in start or the fuel control switch is in run. The engine fuel valve opens when the engine fire switch is in, and the fuel control switch is in run. Both valves close when the engine fire switch is out, or the fuel control switch is in cutoff and the start selector is in norm. Fuel flow is measured after passing through the engine fuel valve. Fuel flow information is depicted on the secondary engine display and sent to the FMS. The oil system provides pressurized oil to lubricate and cool the engine main bearings, gearbox, and accessory drives. The oil system also provides automatic fuel heating for fuel system icing protection. Oil is pressurized by an engine-driven oil pump. From the pump, the oil flows through the oil filter. Next, the engine oil is cooled by a fuel oil heat exchanger. A secondary air-oil heat exchanger provides oil cooling under conditions of low fuel flow or high fuel temperatures. After cooling, oil is delivered to the various components. Finally, a scavenge pump returns the oil to the reservoir. A scavenge oil filter is installed just prior to the oil returning to the reservoir. If the filter becomes clogged, the ICAS advisory message "Engine oil filter, left or right" is displayed. A bypass allows the oil to continue past a clogged filter. Oil pressure, temperature, and quantity are displayed on the engine display. Oil pressure is measured prior to entering the engine by dual oil pressure transmitters. If pressure decreases below the operating limit, the ICAS caution message "Engine oil pressure, left or right" is displayed. Oil temperature is measured prior to entering the engine by dual oil temperature transmitters. If oil temperature reaches the red line limit, the ICAS advisory message "Engine oil temperature, left or right" is displayed. Since oil quantity is displayed only as a value, there is no amber or red line limit. However, a low oil quantity will cause the secondary engine indications to display and the indication to show black numbers on a white background. There are also no operating limitations for the engine oil quantity. As a result, there are no flight crew procedures based solely on a response to low oil quantity. Each engine has a hydraulically actuated fan air thrust reverser. The thrust reversers are operated through the EECs and the reverser isolation valves. The EEC inhibits reverser isolation valve actuation and reverser deployment unless the airplane is on the ground with the engine running. The EECs also control thrust limits during reverser operation. The thrust reversers are controlled with the reverse thrust levers located on the throttle quadrant. The reverse thrust levers can be raised only when the forward thrust levers are in the idle position. When the reverse thrust levers are raised, the EEC opens the reverser isolation valve. A physical interlock located in the aisle stand provides tactile feedback to the pilot, informing when the thrust reverser is or is not deployed. The interlock prevents movement of the reverse thrust lever beyond the reverse idle position until the cowl is partially deployed. When the reverse thrust levers are pulled aft to the interlock position, the auto throttle disengages and the auto speed brakes deploy. When the reverser system is activated, the reverser translating sleeves hydraulically move aft. Reverse is displayed in amber when the reverser is in transit. The fan flow blocker doors rotate into place to direct fan air through stationary cascade guide vanes. And reverse changes to green when the reverser is fully deployed. Pushing the reverse thrust levers to the full down position retracts the reversers to the stowed and locked position. The thrust levers cannot be moved forward until the reverse thrust levers are fully down. The ICAS advisory message "Engine Reverse Limited Left or Right" is displayed if the reverser cannot deploy when commanded or can deploy only with reverse thrust limited to idle. The ICAS advisory message "Engine Reverser Left or Right" is displayed on the ground to indicate a reverser system fault. The caution message "Engine Reverse Air Ground" is displayed when the air-ground logic that prevents in-flight thrust reverser deployment has failed. The caution message "Engine Reverse Commanded Left or Right" is displayed when the left or right reverse thrust lever is not in the down position in flight. The engine monitor unit tracks engine vibration levels. The vibration indications are displayed on the secondary engine display. The vibration source indication, N1, N2, or N3, is also displayed. If the vibration monitoring system cannot determine the source, BB, or broadband, is displayed for the affected engine. Broadband vibration is the average vibration detected. The airborne vibration monitoring feature is intended to track rotor imbalance. There is no certified vibration limit, but when a vibration value of 4 units is reached, the secondary engine parameters are automatically displayed, and the digital vibration readout is displayed in reverse, black digits on a white background. Since there are no operating limits, there are no specific flight crew actions based solely on vibration indication. The Engine Failure Alert System provides alerts when actual engine performance is less than commanded engine performance. Engine fail is displayed on both PFDs and HUDs if actual thrust is less than commanded thrust during takeoff, with airspeed between 65 knots and 6 knots prior to V1. In addition to the engine fail display, the engine fail oral sounds,
engine fail,
and the master warning lights illuminate. The ICAS caution message "Engine Fail Left or Right" is displayed if an engine unexpectedly decelerates to less than idle speed. The message remains displayed until the engine recovers or the fuel control switch is moved to cutoff. The ICAS caution message "Engine Thrust Left or Right" is displayed if airspeed is greater than 6 knots prior to V1 and the engine is producing less than commanded thrust and actual thrust is not satisfactorily increasing toward the commanded thrust, or the engine is producing more than commanded thrust and actual thrust is not satisfactorily decreasing toward the commanded thrust. In addition to the engine thrust caution message, the thrust command arc is filled amber, the master caution light illuminates, and an aural beeper sounds.